Hello, today we will talk about research reactors. We will learn the fundamental difference between a nuclear power reactor and a research reactor. We will also discuss the application of research reactor, get acquainted with the infrastructure, safety principle and fuel cycle of research reactor, as well as the specific of operation and the maintenance of research reactors. We have all heard about a nuclear power plant at least once. We have seen the giant floating towers, cloud generators, a row of reinforced concrete domes, scientifically known as containment, and wires stretching in the different directions like a spider web. All this is the infrastructure of a nuclear power plant, the heart of which is a nuclear reactor. We know well that the main task of nuclear power plant is to generate electricity, and of the nuclear reactor itself is to generate heat. What is research nuclear reactor for then? From the name itself, we can get that its main task is to research. But what can be researched using a nuclear reactor? Let's find out. The very first task of nuclear research reactor was the production plutonium, which is used in atomic bombs. Plutonium cannot be extracted from the Earth's bowels. It is obtained from uranium-238 through neutron capture in a nuclear reactor. Subsequently, research nuclear reactors began to be used to study the interaction of various radiation with matter in the following fields of science and technology: nuclear physics, solid-state physics, superconductivity, neutron scattering, testing of various materials and new types of nuclear fuel for nuclear power plants, production and getting of radioactive isotopes and radiation sources for use in medicine, biology, agriculture, and industry, conducting activation analysis of the composition of materials, minerals, as well as the precise determination of chemical composition and concentration of pollution in our environment, forecasting and substantiation of the service's life and the reliability of critical components and system of nuclear power plant, ensuring their safety. Verification of mathematical models of system and process in nuclear power plant and calculation code. I would like to focus on the popular area of production radioactive isotopes for medicine purpose and manufacturing radiopharmaceuticals. Currently, one of the most common ways to use radioisotopes in the diagnosis and treatment of increasingly prevalent oncological and cardiovascular diseases. The most common isotope used in diagnosis scans is the technetium-99 metastable, used in approximately 85% of all nuclear medicine diagnostic scans worldwide. It is used for diagnosis involving a large range of body parts and diseases such as cancers and neurological problems. Another well-known radioactive isotope used in medicine is iodine-131, which is used as a radioactive label for some radiopharmaceutical therapies or the treatment of same types of thyroid cancers. All these scientific works are possible exclusively thanks to the neutrons produced by research reactor. Essentially, this is the main task of research reactor, to produce neutron. This is the biggest difference between a nuclear power reactor at a nuclear power plant and a research reactor. Most often, the heat that is generated during the operation of research nuclear reactor has parasitic effect and is simply discharged through the cooling tower into the atmosphere. In addition to the previously mentioned applications, research nuclear reactors are also used for training and personal development. Due to their relative simplicity, the high reliability and safety, research reactors are suitable for training reactor operator, maintenance and operation personnel of nuclear facilities, radiation protection staff, regulatory body employees, students, and scientists. When comparing the thermal circuit of a research reactor with that power reactor, they are quite similar. However, due to the low temperature and coolant pressure in the primary circuit, usually up to 19 degrees Celsius, and relatively low thermal power, it is not possible to generate steam to rotate a turbine and produce electricity. Therefore, there is no turbine, electric generator, or condenser. Instead of steam generator, a heat exchanger is installed, through which heat is transferred to the secondary socket, at the end of which a cooling tower is located. Also, there are exceptions. There is a particular feature of research reactor: significant diversity in design, solution, and operating modes, which are determined by the specific purpose and breadth of usage programs. Due to the absence of such metal-intensive elements, research reactor installations occupy much less area than nuclear power plants, and because of much low technical parameters such as pressure and temperature, the process equipment, pumps, heat exchangers, and pipelines are more compact. The thermal power of water-water reactor 1000 is 3000 megawatts, which is the most common power reactor in Russia, while the most powerful research reactor, the ATR located in the United States of America, is 215 megawatts, but the power of most research reactors in less than 10 megawatts. So, compared to nuclear power reactors, research reactors have a simple design, operate at low temperatures, require much less fuel, and therefore produce fewer waste products. Given the important role of research reactor in research and development work, many of them are located on university campuses and research institutes. Since all scientific research on the reactor is related to the interaction of matter with radiation, the materials being studied are usually radioactive and require specially equipped facilities, hot cells, to handle them. A hot cell is a small room with thick concrete walls and a special leaded glass window. Work with radioactive materials is conducted using a remote manipulator. By the way, they are called hot not because of high temperature, but due to the very high radioactivity of the materials in suit. Typically, hot cells are located in close proximity to the reactor in the same building, but sometimes in distant buildings. Of course, as with any other industrial production, waste is generated during the operation of research reactor and during the conduct of scientific work and production. But the waste produced in our case is radioactive. Consequently, it requires special handling. Special developed rules and systems for the collection, processing, and disposal of liquid and solid radioactive waste are applied. A special ventilation system removes gaseous radioactive materials generated during research works. The gas is not immediately released into the atmosphere. First, it may be stored for some time in special tanks and then passed through special filters. A filter passing through the filters cleaner is released into the atmosphere, while the filters are disposed of a solid radioactive waste. To operate a reactor, fuel containing fissile materials is needed, usually in this form of fuel assemblies with uranium-235. During the operation of any reactor, spent nuclear fuel is generated. This cannot be classified as radioactive waste, since it still contained fissile material. The reactor cannot completely burn all the uranium in the fuel assemblies. For Russia research reactor, fuel enrichment with uranium-235 depending on the specific reactor and can range from 19% to 90%. For forming research reactor of Russian design, fuel assemblies are manufactured with uranium-235 enrichment of 19.7%. In this case, the burn-up of 235 can reach 15%. Like nuclear power plants, spent fuel is stored for some time in special on-site storage pool, cooling ponds, and after the residual heat generation has decreased, it is transported for reprocessing to specialized fuel processing plant. The fissile materials is extracted from the fuel, and the remaining radioactive waste is sent for disposal. The extracted nuclear materials is reused in the production of new fuel assemblies. To reduce the proliferation risk associated with highly enriched uranium, which contain more than 20% fissile uranium-235, the International Atomic Energy Agency assists in converting research reactor fuel to low enriched uranium. Also, most research reactors that required highly enriched uranium were built in 1970s for conducting experimental research. Using modern technology, this study can be carried out with low enriched uranium. In the Russian Federation, the design and operation of research nuclear reactors are conducted in accordance with specific regulation titled Rules for Nuclear Safety of Research Reactors. These rules established requirements for the design, characteristics, and operation conduction of research reactor systems and components, as well as organization requirements aimed at ensuring the nuclear safety of research reactor. The rules are developed based on regulatory legal acts of the Russian Federation, federal norms, and rules in the field of nuclear energy use, as well as taking into account International Atomic Energy Agency recommendation regarding the assurance of research reactor nuclear safety. The Federal Environmental, Technological, and Nuclear Supervision Service, Rostechnadzor in Russian, carry out control and supervision over the implementation of these rules requirements. Research nuclear reactors have almost all the same protection system as power reactor. Emergency protection in the form of boron rods, an emergency cooling system, backup power sources, inherent internal safety such as natural coolant circulation, negative feedback that ensure self-regulation and power limitation, low core power density, and low temperature and pressure. A campaign in the operation time of reactor at normal power without refueling the fuel in the core. For a water-water reactor 1000, this time is 18 or 12 months. In fact, this is also the operating time of the reactor between scheduled maintenance. A research reactor, depending on the goal, can operate from 1 millisecond to 3 months of continuous operation. At the same time, the reactor can operate up to 10 years on the first fuel loading or with weekly fresh fuel reloading. Usually, up to 7 specially trained personnel are involved in directly operating the reactor, and more than 100 people are involved in reactor maintenance, research, and production work. To be allowed to operate the reactor, one must have high education in the field of nuclear energy, study technical and regulatory documentation, and undergo training under the supervision of a mentor. In addition, employers annually undergo testing on nuclear and radiation safety, and to maintain the level of knowledge, they take advanced training course every 3 years. When conducting experimental work, special manual tools are most often used, and the automation and the conveyor systems are not utilized, as each task has its own technical characteristics and it conducted in strong ionization radiation fields where complex electronics without protection cannot operate for extended periods. Tools and equipment are designed to be as simple and reliable as possible to minimize the risk of big breakdown and prolonged repair in areas with high radiation doses for maintenance personnel. To maintain the reactor equipment in good condition. Annual schedule preventive maintenance in carried out, and some repair work can be performed in the interval between fuel loading or while awaiting the next experimental work. And finally, some statistics. According to the International Atomic Energy Agency, there are a total of 836 research reactors in the world, including critical and subcritical assemblies. 227 of them are currently in operation, 23 are under development, 521 have been decommissioned, and 75 are temporarily shut down. This concludes my part. Thank you for your attention and good luck.